We are finally getting to the fundamental theorem of calculus. There are two parts to the fundamental theorem of calculus. This first part allows us to find the exact area trapped in the plane between a function and its horizontal axis over some interval that we've been given. The second part is in the next set of videos, and we'll cover what the second part of fundamental theorem of calculus gives us. But what we've done up to this point is we've found several ways to approximate the area trapped in the plane, and this is a way where we find the exact area in the plane. So here it is. If f is continuous at every point on a closed interval, and if big F is any antiderivative of little f on that interval, then the area trapped in the plane using infinitely many rectangles, which is what this is telling us to do. Find the area using infinitely many rectangles, starting at your lower limit of integration A and stopping at your upper limit of integration B. So these are your limits of integration. Your interval endpoints are. Here is your derivative function, right? And f, big F of x, is your antiderivative function. So what fundamental theorem gives us is that we can find the antiderivative function and first evaluate it at the upper limit of integration, and then subtract that result by the same antiderivative function, big F, evaluated at the lower limit. And no more approximately. This equals the exact area. So no longer do we have to approximate. Now, you still need to know how to do Riemann sums, left endpoint, right endpoint, midpoint. You still need to know how to find the trapezoid sum. You're going to have free response questions, multiple choice questions on the exam that cover or that tell you to approximate the area. But now, this notation means for us, when we see this now, in the context of area in the plane, this says use infinitely many rectangles, infinitely many rectangles to add those areas from A up to B, and that will give us the exact area. So now we know fundamental theorem of calculus part 1. Let's use it. Let's work several examples. There'll be a little bit new notation that comes along with this, so make sure you take good detailed notes. So in this example, they're asking us to find the exact area trapped in the plane using infinitely many rectangles, starting at x equal 1, stopping at x equal 2, trapped in between this function and its horizontal axis. So that's done by, we have the integral from 1 up to 2 of x squared dx. Fundamental theorem says find the antiderivative of this function. Well, the antiderivative of that function is 1/3 x cubed. So here's the new notation. We're going to just put a right bracket. We're going to put a subscript of 1 and a superscript of 2 on that right open bracket. So what this notation tells any mathematician that's familiar with calculus is that we have found our antiderivative function and we are fixing to take the step that is fundamental theorem of calculus part 1 in order to find the exact area. So everyone knows what that notation means, so get really comfortable with that. Now the next step that I should see is I should see the antiderivative function with the upper limit of integration plugged into it, minus, make sure that's a minus, the same function with the lower limit of integration plugged into it. Now, if this was a free response question, we could stop right here. That's a real value number. If it was a multiple choice question, the multiple choice answer obviously is going to be in its most simplified form. But this says that over the interval from 1 to 2, the area trapped in the plane in between the function y equals x squared and the horizontal axis is a value of 7/3. That is the exact area trapped in the plane. Here's another example. We're going to talk about the difference between area and total area. Now, area is accumulation. If it says find the area, That is the accumulation of area. Total area says count all area as if positive. So there's a difference between the exact area or accumulated area in the plane, meaning the negative area does subtract from the positive area that's accumulated, and total area, which is count all area as if it was positive. So here's our curve. Find the area and total area between the x-axis and the curve y equals cosine of x from x equals 0 to x equals 3 pi over 2. That is words for telling us to evaluate this definite integral from 0 to 3 pi over 2, the area trapped in the plane between this function and the horizontal axis, or in this case, the x-axis. So we want the accumulated area, which is just fundamental theorem. The fundamental theorem does give us the accumulated area in the plane. So we're going to find the antiderivative. What did we take the derivative of to get positive cosine for the answer? Well, that was positive sine of x. We have found our antiderivative function. We announced to the world we are going to use fundamental theorem. That is the antiderivative function at the upper limit minus the antiderivative function at the lower limit. So the sine of 3 pi over 2 is -1. The sine of 0 is 0. So the signed area, the accumulated area in the plane, trapped between the cosine function, the horizontal axis, over the interval from 0 to 3 pi over 2, accumulates to a value of -1. So let's look what total area would look like. The total area says that I need to count all of this negative area as if it were positive area. So since I know this is going to be negative area, then I need to subtract that interval, and then a negative and a negative will give me that as positive area. Now this area is already positive. I don't need to do anything with that. But the interval from pi over 2 to 3 pi over 2 is going to give me negative area. So I'm going to have to break this up over the intervals where I have positive area and negative area. So this is going to look like just taking the accumulated area from 0 to pi over 2 for cosine x dx and subtracting the interval from pi over 2 to 3 pi over 2 of the same function. And this is going to yield me a negative area. And when I subtract that negative area, then the result will be nothing but positive area. So let's do that. We're going to use fundamental theorem, but we are using the properties of the definite integral to make sure that we are counting all area as if it was positive. The antiderivative on the first definite integral is sine of x. We announce we're doing fundamental theorem. We're subtracting same antiderivative function, and we're doing fundamental theorem over this interval. And so we're going to get the sine of the upper limit, pi over 2, minus the sine of the lower limit, sine of 0. We are subtracting from that, so we'll need to make sure we put a bracket there. The antiderivative at the upper limit minus the antiderivative at the lower limit. That's pi over 2. Hopefully you can see that. So here is fundamental theorem for our first definite integral. Here's fundamental theorem for our second definite integral, and be very careful distributing that negative over here with that negative. So this cleans up to the sine of pi over 2 is 1 minus the sine of 0, that's 0. I'm just going to copy down my negative and put an open parentheses. The sine of 3 pi over 2 is -1 minus the sine of pi over 2, which is +1. So we have 1 minus negative 2. Do you see that? And 1 minus negative 2 is a positive 3. So that makes sense. If the accumulated area is negative 1, then when we kind of break this up over maxes and mins, we would have, here is an area of 1, here's an area of 1, and here's an area of 1. So the accumulated area says that all area up to this x value is going to cancel. We have as much positive as we do negative area, and if we accumulate the area starting at 0 and stopping at 3 pi over 2, we get an accumulation of negative 1. Over here on total area, when we add the area, all of it as if it were positive area, this is positive, and then we count these two units as positive, we get a total area of positive 3. Now, in the context of position, velocity, acceleration, the exact or accumulated area would be displacement. So this is how far away we are from where we started. In displacement, if we started at 0 and we went in the positive direction, right, we have positive area, so we're going in the positive direction till we get to pi over 2, and then we reverse our direction because negative area under the velocity says that we are going to the left. So here we're going to the right, here we're going to the left, and by the time we get to this x value, we're back to where we started from as far as displacement is concerned. And then we continue on for another full unit to go to the left. So that's displacement. For total area, that's distance. So the total distance that we traveled was a total of 3 units. That's what we traveled. It doesn't matter the direction we traveled. It was just the total distance we traveled was 3 units. So hopefully that kind of illustrates accumulated area versus total area. And in the position, velocity, acceleration context, that's displacement versus distance. So I think we'll have time to do this example here. If not, then we'll continue it in the next video. But here's an example of u-substitution for the definite integral using fundamental theorem of calculus. Now, again, u-substitution comes into play when we have something that is being operated on. When we have something that is being operated on, that thing is generally, not 100% of the time, but most of the time, a good choice for u. Remember, we're going to find our differential based on our choice for u, not on what's up here. And so that differential looks like this. Now, I want to equivalently write this integral. I'm really technically right now, while I'm doing the u-substitution, working on the indefinite integral, and then we'll go back and talk about picking up the limits of integration as the final step. So if I have u, here's u cubed, and then du is 2x dx. So du is twice as big as I need it to be. So we compensated for that by popping that constant out front. And now I can rewrite this as u cubed du. I want to take a complicated integral, and the result should be a much more simple integral. Pop your constant out front. Find the antiderivative. Everything that we learned when we were working with the indefinite integral still applies here. So the antiderivative function is 1/8 u to the 4th plus c. Now, I am just going to borrow from this antiderivative function this part of big F. I don't need the plus c. I just need the antiderivative function, and I'm going to back substitute in terms of the original variable. So I'm going to put x squared plus 1 to the 4th in there, and then I'm going to show that I'm fixing to do fundamental theorem. I'll stop right here and pick it up in the next video.